Hello! I hope this video finds you well and that you had a great spring break. My name is Alex Barrios. So this term we will be learning how to prove mathematical statements. Our journey will take us from proving that the square root of 2 is irrational, a statement that we take for granted in our early education, as well as to understand the mind-bending properties of infinity, a notion that we have familiarity with. In calculus we talk about limits as n goes to infinity. But what is infinity? What does it mean to have an infinite set? These are questions that we are going to ponder and investigate in further detail towards the end of our course. And with that, one of the main goals for the term is to familiarize ourselves with the method of proofs. And so the notion of proofs in mathematics can be found in the work of mathematicians from ancient Greece. But it was not until quite recently that mathematics gained a firm footing on the notion of what it means to have a rigorous proof. If we go to the 1700s, yes, they proved results, but from our perspective, those proofs were usually not rigorous, and we are going to do some readings into proofs that were written in that time, and then compare with the methodology that we will cover as part of our course. And so, how did this notion of rigorous proof arise? And it starts actually quite recently in the timeline. And so this dates to 1874 with the work of George Cantor on set theory. And we're going to be discussing this in much further detail in a couple of lessons. And so I'll refrain from talking about the history today about set theory. But in the meantime, I will highly recommend, if you have not done so already, to get a copy of the following graphic novel. So Logic Comics, it's a graphic novel about 250 to 300 pages if I recall, but it follows the life of Bertrand Russell, one of the major players in the foundations of set theory and making mathematics axiomatic, where we can build everything from the ground up. And so Bertrand Russell, amongst his many contributions to mathematics, is his work in making the foundations of arithmetic completely rigorous and precise. And so he, alongside Alfred Whitehead, in 1906, sought to prove that 1 plus 1 equals 2 by defining the integers axiomatically. And they succeeded. It took them 360-ish pages, and here is the actual snapshot of the book, where they prove that 1 plus 1 is equal to 2. All of it is done symbolically, and at the end they conclude from this proposition it will follow, when arithmetical addition has been defined, that 1 plus 1 is equal to 2. Now for our purposes, 1 plus 1 is equal to 2, and the basic axiomatic properties of the integers that we are used to, we are going to be taking that for granted. But one can define the integers axiomatically, and this is what is known as the Zermelo-Fraenkel axioms. And so that's it's a refinement of the work that Russell and Whitehead did, which was rather arduous and difficult, to the point that there is even a joke in the mathematics community that there are only 3 people who ever read Principia Mathematica, namely Russell and Whitehead, the authors, and Kurt Gödel, who would use the work to build up to his incompleteness theorems, which we will discuss later in the course in some detail. But Gödel's work led to the modern foundations of computer science. And this is the fascinating aspect of mathematics. Something as simple as 1 plus 1 is equal to 2, in the work that went into proving it, it led to the modern foundations of our information age. So with that, our goal is to develop your intuition for proving mathematical statements and writing your proofs in English. The goal of a proof is that it should guide the reader to an understanding of the result being proved without taking anything for granted. In particular, we will not make use of words such as obvious or trivial, as these words invoke prior experience of mathematical concepts that are being discussed. For instance, let's think back to when we first learned about adding numbers, multiplying. These are things that we will call trivial or obvious today because we have so much experience with working with addition and multiplication. Yet when we first learned these concepts, it was something that we did not cover in the span of one day, but spent months working at attaining and understanding. And then from there, our math education has built upon that to make it obvious to us today. But as we're learning how to prove statements, I ask you to refrain from using words as obvious and trivial, as we want to make sure that we prove everything without taking anything for granted outside of the assumptions that we will be discussing, what we will call the axioms that we will assume, and from that we will build. Now, our textbook has a lot more material than can be reasonably covered in each video. And my goal is to aim to make videos between 30 to 45 minutes. And as a result, I ask that you read the assigned book readings prior to watching each lecture. And the goals of these lectures are to expand on what is done in the book, with the goal of illustrating what is happening up here. What is the thought process of how we approach a proof? How do we go about writing a proof? And when it's possible, I will provide you with two different proofs of the same statement, so we can see the pros and cons of various different approaches for proving a statement in mathematics. And this leads to our synchronous sessions. The goal of our synchronous sessions is to have you work with others on the homework. Working with others will provide you with the opportunity of seeing how your classmates think about a question. And in turn, they will see how you approach a question as well. Math is artistic and creative. And that's the goal of this course, is to see the side of math that is oftentimes lost in a computationally heavy course, such as calculus. So for example, let's start off with something as basic as addition. And let's look for a pattern in something and ask, how do we go about proving it? So let's go ahead and add odd numbers starting with 1. And so here, let's go ahead and do 1. The next odd number is 3, we get 4. If we do 1 plus 3 plus 5, we are going to get 9. And now what I want you to do is pause the video and do 1 plus 3 plus 5 plus 7, then add 9, 11, and continue in this manner. What do you see? What's the pattern? Formulate a conjecture. So pause the video and work that out. So here are the sum of the first odd positive integers all the way through 13. And what we have is that in each instance we get a square. We have 4, that's 2 squared. If we do 1 plus 3 plus 5, then we get 9, that's 3 squared. Continuing on, we get 4 squared, 5 squared, 6 squared, and 7 squared. And so we could ask, is this always true? Just because we have a pattern doesn't necessarily make it that it will always hold. And so how do we go about proving this? And so that's one of the things that we will develop in this course, is proving the statement rigorously so that it is beyond doubt that it is true and it holds regardless of how many odd integers we add. So one way of visualizing why this is true for now, so we're going to prove this later with what is known as the method of mathematical induction. But one way of visualizing geometrically why this is true is to view this in the following way. So here we have 1, and then we have 3. So I'm putting now 3 circles, and then we have, with the 1 over here, we have 4, and so that's exactly what we have here. So we have a square of side 2. If we do 5, so I'm going to use triangles now. We have 5 triangles, arrange them in this way, we get another square. If we do 7, and now we put in 7 squares, each time we're going to have 3 and 3 for that, and then the final one in the corner will give us the 7th square, and so we get another square. And so we see we have 4 on one edge and then 4 on the other, so we have 16. And if we continue in this manner, we go to plus 9, then we're going to have 4 here, and then a corner one, which will give us the 9th, and then that will add up to a square of each side being 5, so 5 squared, 25. And so that's one way of visualizing this geometrically. But again, we're going to develop the ways of proving this later in the course. But for now, let us ask, how do we go about formulating this statement? We want to make sure that we write everything precisely in English and write it well. Because, for example, we could say something like this. We have 1 plus 3 all the way to n. First n odd integers is a square. But this is going to be this is going to be a bad form of writing this. So we're going to refrain from doing this. So we're not do this. But one way we can formulate this, and I'm going to write this as a conjecture since we haven't proven it. And I'll usually abbreviate conjecture by C, O, and J. So instead of writing it out, I'll just usually write C, O, and J. So we could phrase this as follows. The sum of the first n odd positive integers is equal to n squared. And so we see that here. We had the first 3 odd integers. We got 9, 3 squared. Here we have 4. The first 4 odd positive integers, we get 4 squared, so on and so forth. And so that's one way of formulating our observation. Another way is to write this in terms of a formula. We can use the sum-in notation that we learned through our use of infinite series. And so we can write this as in the following way. So now this is a second variant. We can write that the sum, and I'm going to write this j is equal to 1 to n, and we want to do odd integers, and we want to add the first odd integers starting at, well, we want our index to start at 1 and go to n. So every odd number can be written as 2 times j plus 1. But here I'm going to do 2 times j minus 1, which is another way of writing every odd integer. And this has the benefit that when we plug in 1, we have 2 times 1, which is 2, minus 1, we get 1. Then we plug in, of course, the next term will be 2. We do 2 times 2, 4, minus 1, we get 3. And now we have that this here is equal to n squared. And so we can write this in English as saying the following holds. So the following equality holds. But why the big fuss over proving these statements? Because we can see here that we have a pattern, and it seems to be holding, and we now have a pictorial way of visualizing it. But just because we have a pattern does not necessarily entail that it will hold for every single n. Let us consider the next example. So here we have 4 circles, and I have here n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, where this is referencing how many vertices we have put on the circle. So here we have 2 vertices, here we have 3, 4, and finally we have 5. And now what we are going to do is connect each of these vertices with an edge. So in the n equals to 2 case, we just have the line connecting the 2. In the n equals to 3 case, we're going to have here a triangle. And we're done. Now, for n equals to 4 is where things start to get interesting. So we're going to have here our rectangle. But now we want to make sure that we also connect all the vertices to the other. Because in the n equals to 3 case, this vertex is connected to this and this. But now this vertex here in the n equals to 4 case is not connected to that edge. So let's go ahead and connect them. So we have so here we have our diagonal. And then we also missing this one over here. And so we have so now every vertex is connected to every other vertex. And so we're done. We got that. And let's do that for the n equals to 5. Same thing. And so now we have this here. And now what we want to do is count how many points we can add in the interiors. And so what I mean by this is I can put a point in here. We have 2. Over here we have 1, 2, 3, 4. Here we have 1, 2, 3, 4, 5, 6, 7, and 8. Let's do now the n equals to 5 case. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this might lead us to say, we have now done this for the first, for these 4 cases. Is it always the case if we proceed along this, if we proceed along these lines, that we will always have a perfect nth power of 2? Since we have 2 squared, 4, 2 cubed, 8, 2 to the 4th, 16. Well, it will not hold in general. And actually it fails for the n is equal to 6 case. So here's the case for n equals to 6. We do the same strategy and we end up getting 31. But now we also have a bit of a problem, because we also have, if we zoom in, we notice that there's going to be a black dot going in the interior of this intersection. And so here we have 31. Not a 2 to the nth power. And so this illustrates the need to be precise and not base our expectations on a pattern. Just because a pattern is there doesn't necessarily mean that it will always hold. And so when we see a pattern, one of the things that we want to establish in this course are the tools for how to prove that that pattern in fact does hold. To illustrate the need for rigor in mathematics, let me introduce you to Pierre de Fermat, someone who we are going to be talking about in some length later on. So he was not a mathematician but a French lawyer who did math in his spare time. And in the mid-1600s, around 1640, he said that he had proven the following statement, that if n is a positive integer, then for each n, we have that 2 to the 2 to the n plus 1 is prime. And so we can see over here, we have n is equal to 1. We can plug in 1. We have 2 squared plus 1. Well, that gives us back 5. That is a prime number. Good. N is equal to 2. We'll have 2 to the second, or 2 to the 4th plus 1, which will give us 17. And we continue on in this manner. So here we have it. We have 257, 65,537. We do n equals to 5. We get this much larger number. And now keep in mind, Fermat said he had proven that this is always true. But then in 1737, Euler showed that 641 divides 2 to the 2 to the 5th plus 1, so 2 to the 32 plus 1. So what Fermat said to be a theorem is not even a theorem, it's not a true statement. It is not the case that for every positive integer n, we have that 2 to the 2 to the n plus 1 is always prime. In fact, it is conjectured today that the only primes of this form are precisely the first 4. And so Fermat, basing it off computational evidence, just from these 4 examples, he extrapolated that the rest should be prime because the first 4 are prime. And it is not true. And Fermat had a knack for claiming to have proven theorems in this manner. He based it off numerical evidence and said he had a theorem, yet he never provided a proof. He would write these notes in a copy of his Diophantus's Arithmetica, and he'll write notes in the margin and said, I have a theorem, I have proven this, but the margin is too small to include my proof in it. And later on in the course, we're going to be talking about one of Fermat's big statements, namely what is known today as Fermat's last theorem, which in many ways, modern mathematics owes its development to this statement that Fermat said to have proven, yet it was not until 1994 that it was finally solved. And so we'll talk about that more in our next lesson. But this is just a way of cautioning you to be careful that based on a pattern saying that we have a theorem, we want to be sure that we can prove that these patterns do hold. And so the notion of a theorem brings us to our first topic of the course, which is the notion of a proposition. So by a proposition, we mean a sentence that is true or false, but not both. As part of our lessons, I will use the following abbreviation, DEF for definition. And I'm just going to make a note. The book refers to the first section as sentential logic. This is a term that is not used in the literature, but oftentimes it's referred to as propositional logic or propositional calculus. So I just want to throw that out there when comparing with other texts, or if you take a further course that builds on set theory. When you see the word propositional logic, it's the same as what our text calls sentential logic. And so let's return back to proposition. So we have a sentence that is true or false, but not both. That's the essence of the statements we have covered up to this point in mathematics. Whenever we say a theorem, we have a statement, a proposition, that is true. In the case of Fermat, he had this theorem, which was not a theorem, it was false, but it is still a proposition because the statement is false. For practice, now let us consider the following statement and ask, is this a proposition? So usually we denote a proposition by letters, so P, Q, R. So in this case by P, I mean the whole sentence. This statement is false. And so now, is P a proposition? So if this were a proposition, then it has to be true or false, but it cannot be both. So pause the video and give it a try. Check what happens if it's true. What happens? What happens if it's false? Well, if the statement, which we are calling P, is true, then that means that the statement itself is false. And so then P is false. So P is both true and false. And that's a contradiction. And so I'm going to write this as the following symbol. And we'll talk about this more in the next lesson. And if we were to do the same thing, if the statement is false, then that would mean that if the statement is false, then this conclusion must not hold, so then the statement must be true. Then P is true. And so the statement is both true and false again. And so here we have a statement now that is both true and false. And that right there is what we want to disqualify. So this is not a proposition. So hence P is not a proposition. So this is what is known as the liar's paradox, or a variant of what is known as the liar's paradox. And so this is an instance where we stepped away from talking about a statement about mathematics, as with the previous statement of Fermat, which was incorrect, That was a proposition. Here we have the statement is false. There's no reference to a mathematical quantity. But we could also have statements like the following. We can say 3 is prime. And so this is a true statement. So here, let's go ahead and call this P. Then P is true. So it is a proposition. Whereas if we were to have the statement Q, where we say that 4 is prime, but 4 is 2 times 2, that's not prime, then Q is false. And so it is a proposition, since to be a proposition it has to be true or false, but not both. And so we have this here. But we are not restricted to just talking about statements in math, as I mentioned. We could also have the statement R, where R is Carlton is located in Northfield, Minnesota. And so now this here is also a proposition. And so as part of your homework from 1.1, you're going to investigate various propositions. And the key thing is that they are not restricted to just talking about statements that pertain to mathematics, but we can talk about things in just plain English, as we have here with Carlton is located in Northfield, Minnesota. The next thing we want to do is combine statements. And so this is what we do through connectives. So connectives allow us to combine propositions. And so the first connective that we are going to study is the connective not. And so this is denoted by this symbol right here. And so when we take, if P is a proposition, then we have the not P is defined via the following truth table. And so this is our first example of a truth table. So we have P and not P. So this is the easiest case since we only have one proposition, namely P. P is a proposition, so it's going to be true or false, but it can be both. So we have just two possibilities, true and false. And we define not P to be the negation of P. So if P is true, then not P is going to be false. If we have that P is false, then not P is going to be true. So not P, I lost my screen for a moment. So not P, we can also say in English as the negation of P. So let us go ahead and look at another example. So this is the notion of OR, which is also going to be referred to as disjunction. And the main thing about OR in the way that we use it in math is that if we have two propositions, if P and Q are propositions, then P or Q, this is the symbol for or disjunction, the disjunction of P and Q, so P or Q is true if at least one of P or Q is true. So we can also define this via a truth table. So we define P or Q via the truth table. So we have P. And so now, in the same way that we had P and not Q in the previous slide, we're going to now do P and we'll put Q right next to it. And then we have the one that we are about to define, which is P or Q. And the way we're going to do this is by exhausting the various combinations that we can have, because P and Q are both propositions, so true or false. So we're going to have one possibility is that we have true and Q is also true. We can also have that P is true and Q is false. And we can also have here false for P, Q is true, and false for P, and Q is false. And now for P or Q, it's as a proposition. This connective, here we are defining it as being that it's true if at least one or P is true. So in this case, we have that both are true. This one is true and this one is true. So in each of these cases, we get true. But in the very last one, where P and Q are both false, then we get that this here is false. We also have the connective and, or so the conjunction. And so now here, if P and Q are propositions, we define P and Q to be true if both P and Q are. And so we can go ahead and add that to our truth table over here. So we have P and Q. So in this case, P and Q are both true, so that will give us back true. But now, in the case of P being true and Q being false, we need both of them to be simultaneously true. Oops, I forgot to write true here. And so now this here will be false. And then similarly, here we have this P is false, so this here will be false. And finally here, since both of these are false, we're going to have false. And so we have our truth table. So the next statement we're going to consider is the notion of two propositions being equivalent. Namely, we say P and Q, if they are propositions, that they are logically equivalent if their truth tables are the same. And when this is the case, we will write that P tilde squiggle Q. And so the squiggle here means P is equivalent, logically equivalent to Q. So let's do an example. This is what is one of what are known as De Morgan's laws. And I will do the other De Morgan's law during our synchronous session. So if we do not, and then P and Q, this is logically equivalent to not P or not Q. So how do we go about verifying this? Because now in this setup, the propositions that we are saying that they're logically equivalent are these two. But to build the truth tables for those, we would have to go about it in the same way that we just did in our previous slide. And so let's go through and ask, what do we need to show this? So we, of course, need P and Q. We need P and Q for this one here. We need not P and Q, which we can get once we have P and Q. Oops, and I noticed I put or instead of and. Then we also need not P, not Q, and finally we can do not P or not Q. And so the setup will be exactly as we did before. We're going to have true, true, false, and then true, false, true, false. And that exhausts all the possibilities for P and Q. And so now we go through and populate the table. And the main thing is, we are interested in verifying that this here is the same as this here. And so that's the goal, is to show that both columns are the same, as that will demonstrate that both of their truth tables are the same. So let's start out with P and Q. So we have, in this case, true, but then for the rest we have false in at least one of the columns. So we have that the rest is going to be false, false, false. The negation is just going to be, in the case of true, will go to false, and the false will go to true. So the negation here we have false, and then true, true, true. So now let's look at not P and not Q. And now for not P, we have everything is reversed. So now false, false, true, true. And similarly, we have false, true, false, true. And now we do not P or not Q, which means that at least one of not P or Q, or not Q, that at least one of them is true. And we see that the only time that we have false occurring for both is in the very first entry. And so that will be the only time that this is false. And for the rest of the cases, we have true, true, true. And now we see that we in fact get equality of the truth tables. And so since truth tables are the same, for not P and Q, and not P or not Q, we conclude that they are logically equivalent. And so for the second law, which we will do in our synchronous session, it's similar, except that now we do not, and in parentheses, P or Q. And this is going to be logically equivalent to the not P. And then that or, so for now we can think about that not as distributing over, so we get the not P. But the or becomes an and, whereas in this case the and became an or. And so now we have that this here is not P and not Q. And so that's the second De Morgan's law. And so we'll discuss this one in our synchronous session. And so that's it for the material on 1.1 1.2. In our next lesson, we'll talk a bit more about the grammar laws that the text expands upon. Namely, what is the order of parentheses? Do we have associativity? We want to be careful when we have statements like P and Q or R. What is the order that this is happening? Because it turns out that these statements are not necessarily commutative. And so we want to make this precise. And so the book discusses this in 1.2. And so the plan for our next lesson is to continue 1.2 and move towards 1.3.